All right, discussing question 3. So question 3 is focused on topic 2. Topic 2, which is about digital electronics, and the whole topic of digital electronics carries 35% of the examination. So we have to go fast because we're gonna have to still solve our 2023 and 2022 question papers. So we're still busy with these two papers, and so we're gonna have to go quickly through the module. So the first module in digital electronics, which is topic 2, is module 13, basic digital concepts. So in the basic digital concepts, please, you should study how to explain or describe an analog signal. So you should be able to describe or explain an analog signal. In previous tutorials where we introduced digital electronics, we've spoken deeply into this, so about this. So go and to tutorials and just study, or you can use your textbook, any material that can give you a brief description of what is an analog signal and what is a digital signal. You should be able to describe or explain it. When you are studying, don't forget, because sometimes the examiner would ask you to establish the difference between an analog signal and a digital signal. Please focus on that also when you are studying, and also focus on the waveform, because sometimes the examiner would ask you to represent, making use of a waveform, a digital signal and an analog signal. We know a simple representation of an analog signal would be a sine wave. So a simple sine wave is a representation of an analog signal, and a simple square wave is a representation of a digital signal. So this will be it. So that will be the representation in terms of sine wave. So point 3, go study also advantages of digital system over analog signal. There is a number of advantages of digital system over analog system. Digital systems are easy to understand over analog system. Digital systems are easy to design. Digital systems are user friendly. So go and study the advantage of digital system over analog systems. So study point 4, voltage level in digital circuit. We all know that the voltage level in digital circuit is either logic 0, which represents the lowest voltage, and logic 1, which represents the highest voltage. So that would be it. And study also the negative and positive logic in terms of voltage level. The voltage level, so this was the voltage level. Now, what is a positive logic and what is a negative logic? A positive logic, okay, let me do it here. A positive logic, so in a positive logic, we say that if the number is more positive, so a more positive voltage, so a more positive voltage, a more positive voltage represents a 1, and a less positive voltage. When you have a less positive voltage, you're actually referring to a negative voltage. So a less positive voltage will represent a 0. So we say this is a positive logic. So a positive logic is based on the context that a more positive voltage is representing a 1, and a less positive voltage is representing a 0. So in a negative logic, what do we say in a negative logic? It's just the opposite. So in a negative logic, a more negative voltage, because this is a negative concept, a more negative voltage is going to represent a 1, and a less negative voltage is going to represent a 0. So that's how it is. So you're gonna have to explain this, writing words if they ask you to explain. If they ask you to draw the waveform, you might show something like this. So with a waveform, a more positive. So let's say something that looks like this. Okay, let me draw a signal that looks like this. So this is in a positive logic. Would represent a 0. So if this is our waveform, and this will represent a 1. But in a negative logic, if you redraw the same thing in a negative logic, because here, so you can see that even if this voltage here is below 0, it's less positive. Even if it's below 0, it's representing still our state, 0 state. And because it's more positive here, it's representing the highest state, which is 1. So when you redraw the same thing, let's redraw the same thing with the negative logic. So in a negative logic, this becomes a 1, this becomes a 0. Why? Because we say more negative. So the more this 1 became more, it's below 0, it went more negative it was, so it gave us a 1. And the more positive, because we are dealing with the negative logic, this is the negative logic we're talking about. So in the negative logic, the less negative, which means it's tending to the positive, it's becoming positive, it's actually a positive, but it gives us a 0. So that's how, if you have to represent it with the waveform. So, and you also have to study the general characteristic of a pulse. A general characteristic of a pulse. So this is actually where you have to study the positive going pulse. So there are two types of pulse. So you have a positive going pulse, which means a signal that starts from 0 and there. So from 0 to there. So if you have to label this is a rising edge, this is a falling edge of the signal. So rising edge, falling edge. And then you have a negative going pulse. So in a negative going pulse, it's actually like this. So that's a negative going pulse. So this is a falling edge, that is a rising edge. So you just gonna have to study that. All right, so module 14. So on that was module 13 we just finished. Module 14, you have to study the number systems. Number system, please go through everything. Convert from decimal to binary, convert from binary to decimal. We're gonna have to solve question paper that deals with this. We cannot go through this now. Let's wait until we start question papers. Binary addition, binary subtraction, ones complement. So you go through all of this: binary addition, binary subtraction, ones complement, twos complement, even parity bit. So an even parity bit is a bit that must be added. It's a 1 that must be added to the number, to a word, to make the number either even or uneven. Uneven means odd. So even parity bit, it's a 1 that must be added to a word to make the number even. And odd parity bit, it's a 1 that must be added to a word to make the number uneven. So what does that mean? It means so in computing, actually the computing system doesn't see words, it sees actually binary combination of different binary, and this can represent a word. So for example, here, how many ones do we have in this word? 1, 2, 3. 3 ones. So if they ask you to make this word an even parity, to add an even parity bit to this word, you're gonna have to add a 1 to make the number of 1 even. So 1, 2, 3, 4. Now we have 4 ones, and this is an even parity bit. If they ask you, so if it was like that, so we have the same number 1, 0, 1, 0, 1, 0, 0. That's 3 ones. 1, 2, 3. We're only observing the ones. If they ask you to add a 1, to add a parity bit to make the number odd. So as an odd parity bit. We already have 3, which is an odd number. You don't have to add anything. You just write a 0 there. So most of the time they will ask you to explain what is an even parity bit, what is an odd parity bit. But sometimes they will give you a number and they ask you to add a bit to make it even or to make it odd. So that was it. Module 15, you have to go through the logic gate. In the logic gate, what do you have to study? You have to study the symbol of the logic gate. We're going to talk about this. The Boolean expression for the logic gate, the truth table of logic gate, and the circuit diagram of logic gate. There is circuit diagram that represent each logic gate. So when we are discussing module 15, we're going to talk about this. And then module 16, it's on the flip-flops, and there is a ridiculous number of things that we have to go through. You should be able to explain operation of an RS flip-flop, draw the diagram of an RS flip-flop using NAND gate, draw the diagram of an RS flip-flop using NOR gate, draw the symbol of an RS flip-flop, draw the truth table of an RS flip-flop, draw the diagram of a clocked RS flip-flop. This was all for just the RS flip-flop. And there's the seventh one. The seventh one is draw the IEC symbol of an RS master slave flip-flop. There is a circuit diagram, but this circuit diagram for the RS master slave flip-flop is gonna be huge. I'm not expecting the examiner to ask that large circuits for you to draw it, but yeah, if you can study it, it's good also. So if you can study the whole diagram, but usually they will ask you to draw the IEC symbol. Explain the operation of a D-type flip-flop and draw the truth table of a D-type flip-flop, and then draw the IEC symbol of a D-type flip-flop. Should be able to explain the operation of a T-type flip-flop and then draw the IEC symbol of a T-type flip-flop and draw the truth table of a T-type of a T. This is a T-type. Sorry, it's not a D. We did D here already. So this is a T-type flip-flop. So draw the truth table of a T-type flip-flop. 14, you should be able to explain the operation of a clocked JK flip-flop. You should be able to draw. Usually they will ask you, this question I've seen most of the time, usually they will ask you to draw the IEC symbol of a clocked JK flip-flop. You can also study how to draw the truth table. After you've been able to explain, you should be able to draw the truth table of a clocked JK flip-flop. So we're going to go straight to the question papers and try to solve some of these questions. All right, so this is a question paper. It's still a 2023 question paper, so we are still working on 2023 question paper, and we have downloaded this paper from NCV exam papers. So if you just type NCV exam papers from your app stores, you should be able to download this question paper on your phone, of course. So 2023 question paper, question 3. We're solving question 3. So differentiate between analog and digital signals. Analog and digital signals. So we've discussed about this, analog and digital signals. So you will notice in our guideline here, as we're discussing, this is module 13, basic digital concept. So you have to explain the difference between an analog signal and a digital signal, as we know that an analog signal has value at every time instance. So value at every time instance, and it has value at specific. This is every time instance. This is specific, has a value at specific time instance. So that's it. Sometimes the examiner would ask you to represent the analog signal and the digital signal into waveforms. So we've discussed about that. 3.2, explain how voltage levels are used to represent bits. So we also discussed this. So 0 or logic 0. So logic 0 represents the lowest voltage, low voltage, and logic 1 represents high voltage. So that's it. So that's how voltage levels are used to represent bits. So 3.3 converts 342 base 10, they write here base 10, to binary. So base 10 means we are converting a number from decimal to binary. So I'm gonna have to add a new page. So we are converting 342 base 10, which means decimal number, to binary. So different methods can be applied to convert this. So the easiest method we have adopted with students, this seems easier for them, so we go with that method, is this method of drawing the table. So we draw the table and we start putting the lines until, so the columns are there. So I don't know how many of these lines these vertical lines do I have to draw until I start filling up. So 2 to the power 0 gives me 1, 2 to the power 1 gives me 2, 2 to the power 2 gives me 4, 2 to the power 3 gives me 8, 2 to the power 4 gives me 16, 2 to the power 5 is, you have to use a calculator when you're struggling. Please use a calculator every time you're struggling. 2 to the power 5 is actually 32. 2 to the power 6 is 64. 2 to the power 7 is 128. 2 to the power 8 is actually 256. That will be correct, yes. And then 2 to the power 9 is actually 512. So what do you notice? You notice that 2 to the power 9 gives us a number that is far bigger than the number we want to convert. We want to convert 342 from decimal to binary. But 2 to the power 9 gave us a number that is bigger than 342. So which means we don't have to consider 2 to the power 9. So 2 to the power 9 is far higher for us. So we have to stop when the number is closer or equal to the number that we want to convert. For example, if the number I wanted to convert was 162. So 162 is the number that I want to convert. I will have to stop at 2 to the power 7 because 128 of 2 to the power 7 is the closest number to, closer and smaller to 162. If the number I wanted to convert is 61, so 61, the smallest and closest number to 61 is 32, 2 to the power 5. So I will have to stop at 2 to the power 5. So I'm giving all these examples so you know when to stop. So I will stop at 2 to the power 5 because if I go 2 to the power 6, the answer is 64, and 64 is bigger than this number. So if I wanted to convert 18 into binary, so 18, I will have to stop at 2 to the power 4. 2 to the power 4 is 16. 16 is smaller and closer to 18. So if I go 2 to the power 5, that's 32. 32 is bigger than 18. So this is for you to know when and where to stop. So for 342, we're going to have to stop at 2 to the power 8 because the answer is 256. That's the small and closest number to 342. Now, what do? The next thing you do is, which numbers of all these numbers obtained after doing 2 to the power, which number, if you combine them together by adding them up, will give you exactly 342. So we can try that on the side. So if we take 256, if we combine it with 128, that's gonna be far. That's gonna be like 500 something. 128, that's gonna be like 168, and then 3. That's 384. That's bigger. That's far bigger. Yes, that's far bigger. So we want to choose a number that's smaller, or we want to combine numbers to get exactly 348. So 52, we can try plus 64. That gives us 0, that gives us 1 there, and then 2, and then 1, and then 3. That's 320, which is still smaller. So plus 32, it's going to give me 356, that's bigger. Plus 16, it's going to give me 336. It's smaller, and we're getting closer to 342. Plus 8. Plus 8 is going to give me 344. That's bigger. That's bigger than 342. So we're now going to take 8. We're going to take plus 4. Plus 4, it's giving me 0 here, 1, 4, and 340. And then plus 2, it's giving me 2, 4, 3. So you can see that's the number that we have used. We have used 256. We're going to put a 1 there. We have used 64. We're going to put a 1 on 64. We have used 16. We're going to put a 1 on 16. We have used 4. We're going to put a 1 on 4. We have used 2. We're going to put a 1 on 2. The rest of the numbers, like 128 takes a 0. 32 takes a 0, 8 takes a 0, and then 1 takes a 0. So the final answer, 342 base 10, gives me 101010110 in binary. So that is your final answer. That's how you convert. This method is much easier. Feel free to use a method that works for you. But with students, we have been going through different methods, and they concluded that this one was very simple for them. It's actually illustrating everything, so it's much easier. So that is our final answer. Let's go back to the question paper. So the next one is add 110 base 2. There is the 2. 101. They're supposed to be base 2 there. That's an examiner issue there. So there was a typing mistake, I assume. So 110 base 2 to 101 base 2. So we are doing addition here, and this is very easy. So addition. So binary addition. So this is binary addition. We have discussed that also. Binary addition. So before you do any binary addition, you have to adhere to the rules. So the rule says that 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1 is 10. This is binary. If you come to decimal, when we're doing our decimal in primary school, 1 plus 1 was 2. So 2 in binary is actually 10. That's why our answer is 10. But what does the rule say? The rule says first you're going to have to write a 0. First you're going to have to write 0 and carry 1 over. So that's what you do. So this is the rule. If you follow this rule, you will not falter. You will not make a mistake when you're solving a problem. Now, back to the question. What was the question? The question said 110 base 2 to 101. So 110 base 2 to 1. So we are doing 110 base 2 plus 101. Both of them are base 2 actually. So the best way to solve this question is to rewrite this vertically. First number 1 1 0, and the other number underneath vertically 1 0 1. So just like that, and then we put a plus there. Now we're following these rules. 0 here, 0 plus 1, 0 plus 1 is 1. So 0 plus 1 is 1. 1 plus 0, 1 plus 0 is 1. So 1 plus 0 is 1. 1 plus 1, so this is the rule. 1 plus 1, it's actually 1 0. Since this is the last number, you can just write 1 0. But if we follow this, first write 0. So we write a 0. Then carry 1 over. We're going to carry 1 over. But there is nothing to edit with here. So what we do is we just come and then we bring that 1. We drop it here. So that is our final answer. 110 plus 101 is actually equal to 1011. Correct. So next question. Subtract. Okay, this is going to be a little bit challenging. Subtract 11010 from 1001 by using 1's complement. So here we're going to use 1's complement. So solving this question, I'm going to do my best to solve this question using 1's complement. I'm going to use the question for 1's complement, and I'm going to, in case a question on 2's complement is asked, you know how to use the same question. 1's and 2's complement. Why do we use 1's and 2's complement? 1's and 2's complement. So 1's and 2's complement. 1's and 2's complement. It's just a method. It's only a method of solving subtraction problems using addition. That's what we do here. We solve here with 1's and 2's complement. We solve subtraction problems using addition. So that's what we do. We solve subtraction problem using addition. So it's because in some cases in computing, some mathematical problems, some arithmetic problems, when the computer solves some arithmetic problem, it uses some of these methods. So we're trying to solve subtraction problem using addition method. A subtraction problem would be, for example, subtract 1001 from 1101. So we have this type of problem. I just selected a very simple problem. So 1001 from 110 using 1's and 2's complement. So we're going to use the 2 methods directly one time. So 1's and 2's complement. So what does that mean? It means this is a subtraction problem. Subtract 100 from 1101 means we are doing 1101 minus 1001. That's what we are doing. So this is a subtraction problem, but we must solve it using addition method. But how do you get to solve this problem using addition method? The first step, so if we are using 1's complement, so in the 1's complement context, the first step in a 1's complement problem, the first step will be to take the number after this number after the minus sign. write its complement. Writing the first complement means writing the opposite of each one of these numbers. So the number is 1001. So on 1's complement, what do you have to do? You write the opposite of each one of these digits. 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, and then 1 becomes a 0. This is the first complement. That's the first complement. Now, since we are only using 1's complement, we're going to stop at the first complement. So that's your first complement, which means after you obtain the first complement, what do? You take your first complement, you add it, because the problem that was given to you was a subtraction problem, but since you took the second number after the minus, converted it into its first complement, and you obtained this. Now what do? When you obtain the first complement, you must now take your first complement and then add it to the first number before. So that's what you do. So you're gonna take 1101 plus, instead of doing minus, you're gonna use plus, not this, but the complements that we obtained here. That's what we do. Plus 0110. So that's what we do. So we're using a plus here. And now remember the rule of subtraction, where for addition, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 1, 0, but they tell you to write a 0 and carry 1 over. That's what they tell you. So we're going to apply the same method here. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1, we have it here. 1 plus 1, it's a 0, and we carry 1 here. Now 1 plus 1, it's another 0, and we carry 1 here. Do you notice that this 1 here that we just carried here is an excess? So because we have 4 digits here, we cannot just drop this 1 here. It's an excess. It's going to create a number with 5 digits. So we don't want to create a number with 5 digits. What do? We take this excess 1, then we carry it over, and then we take it and then we add it back to this answer that we got here. So 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1, and then 0 plus 1 is 1, and then this 0 is just going to drop there. It means nothing. So this is our final answer when it comes to 1's complement. I believe that was simple. Okay, now we solve the same question using 2's complement. So for 2's complement, so if we are solving the same question using 2's complement, so pay attention here. So we're solving the same question using 2's complement. So our question is 1101 minus 1001. So to get to the 2's complement, the first thing you do is you take this second number here, you first convert it into its first complement. That was 1 becomes a 0. So converting into a first complement means that writing the opposite of each digit. So we take the second number after minus, second number here after minus, the number after minus. So we convert it to its first complement first, because before you get to the second complement, you must first achieve the first complement. So to achieve the first complement, you write the opposite of each digit of the number after comma. So 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, and then 1 becomes a 0. So this number here is the first complement. Now remember, we have to get to the second complement. So first complement. This is the first complement. Now to get to the second complement, you must take this number that we got, the first complement, plus 1. So you take the first complement. If you take the first complement plus 1, it gives you the second complement. So first complement plus 1, you get 0 plus. Remember the rules of addition. 0 plus 0 is 1. 1 plus 0 plus 1. Let me take it in order. 0 plus 1 is 1. 1 plus 0 is 1. Sorry. There's a mistake there. So remember the rule of addition. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1, and then 1 plus 1, it's 1, 0. We said you write 0 and carry 1 over. So that is what we do there. So in this case, we just have one line. 0 plus 1 is 1. And the rest of the number, 1 plus nothing is 1. 1 plus nothing is 1, and then it is 0 there. So this number here is your second complement. This number is your second complement. So I'm going to repeat here. To obtain the first complement, you write the opposites of each digit of the number after the minus. That's the first complement. To write the second complement, you just add a 1 to the first complement's number, and the answer that you obtain is your second complement. Now that we have obtained the second complement, what do? We take the second complement, we add it to this number here. So that's what we do. We take the second complement. Same thing we did when we were doing one's complement. We took the first complement, we added it to the number that was given to us initially. That was we're supposed to subtract from. Now that we got the second complement, we do the same thing. We take the second complement, we add it. Instead of subtracting, we are going to add. So we're going to have 1, 1, 0, 1 plus 0, 1, 1, 1. That's our second complement's number. So that's what we do. So we're still following our rules of addition. I can rewrite it here just for us to see it. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1 is 1, 0. But we must write 0 and then carry 1 over. So that's it. So we do the same thing. We follow the rules step by step. 1 plus 1, we said it is 0. And we carry 1 over. We're going to carry that 1 there. And then 1 plus 0 is still 1. So 1 plus 1 here, it is 0. We carry 1 over. Now we have 3 1s following each other like this. It's much easier. So we first do the first 2. These two here. So 1 plus 1, it is 0. But we carry already. Then we come back here. We continue. 0 plus 1 is 1. So and then here again. 1 plus 1, it is 0, and we carry 1. Now here's the magic that happens with 2's complement. In 2's complement, you just have to ignore the last carry. Ignore it, so it doesn't count. Just leave it. So your final answer is this one. If you check, you're going to see that it's the same answer that we obtained when we're doing 1's complement. So as we said, 1's and 2's complement are just methods that are used to solve subtraction problem using addition. You're going to obtain the same answer. You should obtain the same answer if the same question is given to you in 1's or in 2's complement. You should obtain the same answer. So with 1's complement, we obtain 0, 1, 0, 0. With 2's complement, we also obtain the same answer. So in conclusion, if I'm given, for example, 1, 1, 1, 1 minus 1, 0, 0, 0. So if I'm given this in conclusion and I'm asked to solve that problem using 1's complement on one side, 1's complement, and 2's complement on this side, first of all, I must take this number 1000, first convert it. For one's complement, it's very easy. What do I have to do? I just take 1000, I convert it to its first complement. 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 0 becomes a 1. That's it. But here, I take the same number, I must convert it to its second complement. It's 2's complement. First of all, I go with 1000. In the first complement, it's 0. It's 0 becomes a 1, 0 becomes a 1, and then 0 becomes a 1. And I add a 1 to convert it to its second complement. And then here, 1 plus 1 it is 0 carry 1, and then 1 plus 1 it is 0 carry 1, and then 1 plus 1 it is 0 carry 1, and then 1 plus 0 it's a 1. So this is the second complement of that number. This is the first complement of that number. So what do I do now? After I've obtained the first complement of that number and the second complement of that number, what do? I add it. So I'm going to take that number, I'm going to add it to 1. Let me create some space because I'm going to have a lot of carries here. 1, 1, 1, 1, plus, instead of subtracting, 0, 1, 1, 1. So there. And here, I'm going to take the second complement, I'm going to add it also. 1, 1, 1, 1, plus 1, 0, 0, 0. So, on one side I'm solving 1's complement, on the other side I'm solving 2's complement. You should be used with the rules now. So 1 plus 1 it's a 0 carry 1. That's a 3 1. So 1 plus 1 it's a 0. I'm going to carry the 1 already, but I come back here. 0 plus 1 is 1. I have 3 1s again here. 1 plus 1 it's a 0. I'm going to carry the 1 and I come back here. 0 plus 1 is 1. And here I have 2 1s. 1 plus 1 it is 0. I'm going to carry 1 and then I come 0 plus 0 it's a 0. Now I have a carry. In 1's complement, what do? You take the carry, you swing it over, and you add it to the answer that you got previously. So that's what you do. So 0 plus 1 is 1, 1 plus 1 is 1, and then, 1 plus 0 is 1, and then 1 plus, that's your final answer, and 0 there. So that is your final answer. We're supposed to obtain the same answer here. So if we add this, what do we obtain? 1 plus 1, it's a 1. 1 plus 0, it's a 1. 1 plus 0, it's a 1. 1 plus 0, it's a 1. 1 plus 1, it's a 0 carry 1. And what does the rule say for 2's complement? Ignore the carry. Ignore it. So once we ignore it, we realize we got the same answer. So I did this like this, so it's much simpler. All right, so back to the question. 3.5, we are solving 3.5. Subtract 11010 from 1001. So we are actually solving. We're actually doing the actual question is actually 1. This is 3.5. So it's actually 1001 minus 11010. Let me just verify to make sure it's correct. So yes, there it is. So 11010. So one thing you notice is that 11001 has 4 digits and 11010 has 5 digits. So I can rewrite the same question, just equalizing the number of digits by adding a 0 before here, just to keep a balance. 1 0 1 0. So I rewrote the same thing, but nothing changed. I just added a 0 here just to keep up with this number, which has 5 digits, minus 1 1 0 1 0. The question says we should solve using one's complement. We are using one's complement here. So I promised that I was going to use one's complement and solve it first using one's complement, and I'm going to solve it later using two's complement. So let's start. So what am I doing? I'm going to take the second number here, convert it into its first complement. Simple, just by writing the opposite of each digit. 0 becomes a 1. 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, and then 1 becomes a 0, and then 0 becomes a 1. So what do I do next? I take this number and I'm going to add it to the previous number there. So 0, 1, 0, 0, 1 plus 0, 0, 1, 0, 1. That's what I do. So you can even see that was necessary for me to add the 0 there, because you can even see that each digit is standing right on top of the other one. So it makes it so simple for me to solve my problem. Don't forget our rules, which is still valid. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 1, 0, but you're supposed to write a 0 and carry 1 there. So we apply the same rule. 1 plus 1 is a 0, carry 1, and then 1 plus 0 it's a 1. So 0 plus 1 it's a 1, and then 1 plus 0 it's a 1, and then 0 plus 0. Have you noticed that most problems that we solved earlier, most one's complement problem that we solved earlier, we're having a carry as the last. Did you notice that we had to take the one that was here and then swing it and add it here? But in this case, we don't have that case. We don't have a last carry. There's no last carry. One's complement should have a last carry. There's no last carry. What does this mean? It means we are dealing with negative numbers, but that's not your concern. Don't be concerned about negative numbers. So when there is no carry, what do? Complement again for this. Do the one's complement again. Take the last answer that you obtained, do the one's complement of that answer. So if you do the one's complement, so 0 becomes a 1, and then 1 becomes a 0, 1 becomes a 0, 1 becomes a 0, and then 0 becomes a 1, and that is your final answer. So that's it. That's your final answer. So I believe you guys will remember. So when you finish solving your one's complement and there is no last carry, it means you are dealing with a negative number. So what do you have to do? You take the last answer that you obtained, you do the one's complement if they ask you to do the one's complement. When we're going to solve the two's complement, we're going to take this last answer, we're going to two's complement it. So let's move on. So we're going to take the same example. We're going to compare the two answers. We're going to take the same example, which was 1, 0, 0, 1 minus 1, 1, 0, 1, 0. We said we're going to use now two's complement. We're going to use two's. This question, there was not question with two's complement, but I just want to use it for your own benefit. So we said this one has 4 digits and this one has 5. We can balance by adding a 0 here. So we're going to just add a 0 there. So this second number here, this one here after the comma, that's the one we're going to complement. So what do? First we complement. We do first the first complement. So we write the opposite of each digit. So 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, and then 0 becomes a 1. That was the first complement. The second complement, what do? We just add a 1 on the second complement. 1 plus 1, it's a 0, carry 1. 1 plus 0, it's a 1, and then 1 plus nothing is there, it's a 1 there, it's a 0, it's a 0. So now we take this second complement number, we're going to add it to the first number that was given to us there. So that's what we do. So what do? We take 0, 1, 0, 0, 1 plus 0, 0, 1, 1, 0. So that's what we do. And then So we do a plus there. That's a plus. So 0 plus 1 is 1. 0 plus, so that was 1 plus 0 is a 1. 0 plus 1 is a 1. 0 plus 1, it's a 1 there. 1 plus 0, it's also 1. 0 plus 0, it's a 0. So now that we have it like this, there was no carry also. Remember, with 2's complement, if there is a carry, you're supposed to ignore the carry. But there was no carry here. There was nothing here to ignore. So when you have case like that, remember, it means you are dealing with a negative number. But don't worry about that. All you have to do is take your last answer that you obtained, complement it again. So now that we are dealing with the 2's complement, we're going to complement this number to its second complement. So the first complement consists of converting each digit to its opposite. So 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, 1 becomes a 0, and 1 becomes a 0. And now to its 2's complement, what do you have to do? You just have to add a 1 to it. And then you have 0 plus 1 is 1, and then 0 plus nothing, it's a 0 there, it's a 0 there, it's a 0 there, and it's a 1. So that is your final answer. Is it the same as the 1's complement? It's supposed to be the same. Yes. So it's 1001 for the first complement that you obtain, and it's also 1001 for the second complement. So that's how you solve that question. I just did the 2's complements just for you to be aware that they might ask this type of question with 2's complement. All right, 3.6, define the term even parity bit. So we have discussed about even and odd parity bit. Even parity bit, the extra 1. So the extra 1 that must be added to the word to make the number even. And odd parity bit, the extra 1, like 1, that must be added to the word to make the number uneven or odd. So that's actually the definition. So we go back to 3.7, draw an AND gate switching circuit and explain its operation. So we're going to see 3.7, 3.8, they say actually draw the IEC symbol for the following gate. So let me explain the gates. Let me go to the gate. Okay, so we have our 7 gates. So there are gates which are like positive, and there are gates which are negative, which means they are just the opposite of the other one. So we start with the NOT gate. NOT gates. So what you have to know about the gates, in my guideline here, if you remember about the logic gate, what do you have to know? You have to know the symbol of a gate. A logic gate, we have 7 of them. You have to remember the symbol of each one of them. I'm going to explain the symbol now. Let me try to explain the symbol. So the symbols are very simple, except for the NOT gate, which only has 1 input. So the 1 input is going to be this one, and the output we can assign X as the output. The rest of the gate have 2 inputs. So you have this with 2 inputs here, and they are very easy. You just have to draw a box like this, 2 inputs, 1 output. Draw the box, 2 inputs, 1 output. And now you draw another box, 2 inputs. I'm first drawing the positive one. You're going to see what I mean here. 2 inputs, 1 output. So you can label your input as A, B, and the output is X. It's no problem. A, B, or you can choose any labeling. But this has been the standard. So people have been labeling like this: A, B, and your output is X. And as for your information, this representation of logic gates, it's only happening for like in your program, because you will notice in other countries or in other programs they have a different representation of logic gate. So this representation, so for you in your program, for you to pass your exam, you have to represent your logic gate exactly the way you studied them. So this is the representation we do for the symbol of each logic gate. So so there they are. Now they have different name. We have AND gates. So an AND gate will have an AND symbol inside it. An OR gate will have a greater or equal to 1 symbol inside it. An XOR gate will have equals 1 as a symbol inside it. So that's very simple. Now NAND, because you have here AND gates, so here you have an AND gate, and the opposite of AND is NAND. Here you have an OR gate, the opposite of OR is NO, and then you have a XOR gate, the opposite of XOR is XNO. So look how the representation in symbol is going to be. So an AND gate is going to be a box with the symbol AND inside, and NAND gate is going to be exactly the same thing, 2 inputs A and B, but on the output you negate it, you put a small knob there and then you put your output. So that's how your output is going to be. So and then the AND symbol is there. So the only difference is on the output where you have to negate it. So same thing here. So your OR gates is gonna be like this. So your NOR gate is gonna be the same thing, 2 inputs A and B, and your output, so your symbol inside is exactly the same, but it's your output that needs to be negated, and it's like that. And same thing with your XNOR. Your XNOR also, you're gonna have 2 inputs A and B, and the symbol inside is equal to 1, and you just have to negate it there. So that's it. That's how it's going to be, and it's X there. So that's the first thing you have to know. Drawing the symbol, it's easy to remember them. AND and NAND have an AND symbol inside. OR and NOR have a greater or equal to 1 symbol inside. XOR and XNOR has equals 1 symbol inside, and so that it should be easy to remember. The next thing you have to know about the logic gate is the Boolean expressions. So like each output has an expression to it, so it has an expression assigned to it. You can see in my note here there is a symbol. So what you have to know, AND means multiplication. OR means addition. So let me not circle it, because circling also in logic, in digital electronic, means a lot. So AND is actually a multiplication sign or a dot. Those are multiplication. Now OR is addition. XOR is plus circle. This is exclusive. You circle it. So when you are writing your expression for an AND gate, is going to be X is equal to A and B. So that's how you read it actually, A and B. But yeah, for a better understanding, we can say A multiply B. And then when it's the opposite, which is the NAND, A multiply B and a bar on top. So that's the negation that you put there, a bar on top. So same thing with the OR gate. So you're going to have this expression plus, which you read X is equal to A or B. And then you come here, you're going to read the expression A or B bar. So there's a bar on top. And same thing with the XOR, which is the A exclusive B, and then A exclusive B bar. So that's how it is. That's the expression. So you have to remember also the expression, but I have not seen really a lot of expressions in exam papers. What I have seen a lot is the truth table. The truth table, remember the truth table. They might ask you to explain using the truth table. So that's something you have to know. You must know the truth table for each gate. By the name, before even I explain to you the circuit diagram, from the name you can already tell what it does. A and B. Remember, in digital, 1 is the highest logic. 1 is the highest logic and 0 is the lowest logic. So, and for you to obtain the name AND gate, for you to obtain a 1 in the output, A and B must both have a logic 1. That's the name. A and B. A and B must all have a logic 1 there. So for you to obtain a 1 in the output here, A and B, A and, the name AND means the input A must have a logic 1, the input B must have a logic 1. A and B must have a logic 1, and you're going to have a 1 in the output here. That's how it works. The rest, it's going to be zeros. So if only one of them has a different logic, it's zeros everywhere. So NAND is going to be the opposite. So where you obtained a 0, it's going to be a 1, 1, 1, 1, 1. And where you obtained a 1, it's a 0. That's how it works. So OR gate. Oh, what does OR mean? OR means for you to obtain a 1 in the output here, A or B, any one of them, if only any one of them has a logic 1, or both of them have logic 1, that's how you obtain a 1. So if they have nothing, if they have a lowest logic, it's a 0. If A or B has a logic 1, it's a 1. A or B. If also both of them have a logic 1, it's also 1. That's how it is. So the no is going to be the opposite of what we did here. No is going to be, everywhere you obtained a 0, it's going to be a 1, and the rest, it's going to be 0, 0. That's how it works. Now, XO. What does XO mean? XO means that for you to obtain a 1, A or B, A and B must have different logic. So let's check where A and B are both having different logic. These are the two possibilities. A and B are having different logic. You're going to see the first one here. B is having a different logic. A is 0, B is 1. Then you obtain a 1. Here, A is 1, B is a 0. Then you obtain a 1. If they have the same logic, it's a 0. It doesn't matter if it's a 1. If they both share the same logic, like here they say they share the same logic, that's a 0. Here they say they share the same logic, that's a 1. It's still a 0 on the output. So for you to obtain a 1 in the output, both inputs must have a different logic, opposite logic. Now, the opposite is going to be both of them should have the same logic for you to obtain a 1 in the output. If they have opposite logic, it's 0, 0. That's how the truth table works. Now, circuit diagram. So usually when they ask you to remember the diagrams, your program only covers the diagram. I'm back to the guideline. Your program only covers the diagram for. So we're not going to exaggerate. We will follow exactly what your program says. Your program only provides the diagrams for NOT gate, AND gate, NAND gates, OR gates, and NOR gates. They don't provide for XO and XNO. So we're not going to put you into trouble since we are just preparing the exam. We don't want to go through there because they will not ask you to come up with a diagram, circuit diagram for XO and XNO. They will usually circle around the first 5. So let's explain each one of them. So here we did not complete the truth table for a NOT gate. A NOT gate is an inverter. So when you give it a 0, we give it a 1, it gives you a 0. When you give it a 0, it gives you a 1. That's how it operates. If you put a 1 in the input, you get a 0. If you put a 0, you get a 1. So how does the circuit? So there is a question where they are asking you. This question here, it says, explain 3.7. Draw an AND gate switching circuit and explain its operation. So when it comes to circuit diagrams of logic gates, I can give you a hint. AND, except for a NOT gate. A NOT gate is actually, let me do a NOT gate. A NOT gate is actually an inverter. So what does it mean? It means that you have a bulb there, that's the bulb, which has a switch, and guess what? The switch is in parallel with the bulb. So your circuit is actually like this. That's the supply. So what happens here? If you have a truth table, you're gonna notice your bulb is the X, your switch is the A. So what do you notice here? When your switch is open means 0, your bulb is already on, because this is how your current is traveling here. Your current, let me change the color. Let me take color blue, or let me take a highlighter. Your current is traveling there and it's completed circuits there. Closed circuits. So when your switch is open, your output is already 1. Your lights, your bulb is already on. It's 1. But when you close the switch, what happens? You short circuit your light. It's like you are having your light like this. You just take the 2 pin, you short circuit them, then you put the battery. So your plus and minus of your battery are being joined together by the switch. That's what happens. So what happens? You get nothing in the output, 0. That's why it's an inverter. So when there is nothing, when you give nothing to it, the light is on. When you give something to it, when you close the switch, then the light goes off, because the lights find themselves being short-circuited. So that's how they operate. Now, let me give you a hint now when it comes to AND. We know that AND and NAND, they are complementing each other. And then OR and NO. So let me give you a hint in terms of circuits. OR and NO. So for an AND, your switches are in series. And for a NO, OR and NO, your switches are in parallel. That's exactly what it is. So for an AND, your switches are in series. Let me take a normal. AND and NAND, your switches are in series. Let me take a normal one. AND. So for your AND, you have switch 1, which is input A, and in switch 2, which is input B, and then you have your bulb there, and then that is your supply. So plus minus. If your switch 1 is A and your switch 2 is B and your light is X, when will your lights turn on? If all the switches A and B are all closed, then your light is on. That's the only time your light is on. If switch B is open and switch A is closed, your light is not on. If switch A is open and switch B is closed, your light is not on, because the flow of current is not complete. The circuit is not closed. So your switch is not on, your bulb is not on if one of them is open. The only time your bulb is on if both of them are closed. If you recheck our truth table, you're going to notice that is true. The only time you have a 1 in the output is if input A and input B are both on. So if these two switches are all closed there, then your output X is on. If they remain open, your output is, when they remain open, your output is 0. Or if one of them is closed, the other one is open, your output also is still 0. Now, the NAND, how does the NAND operate? For your NAND, your switches are still in series, but both of them now in parallel with the lights. That's what happens. In series, but in parallel with the light. So you end up with something that looks like this. So if you recheck our truth table, back to our truth table, you're going to notice for your NAND gate, if both switches are on, that's the only time the light goes off. For all the possibilities, for all the eventualities, your light is still on. If both of them are open, check how. Let me take the highlighter. Check if the two switches are open, your current flow goes this way. Current comes here, and then it's gonna go, because the switches are open. On top there, the switches are open. It won't go through, but it can go through here, through the light, and back to the negative. So when the two switches are open, when the two switches are 0, the light is on. Even if one switch is closed, if A, this is A, this is B. If A is closed and B is open, same thing is happening. If A is open and B is closed, same thing is happening. The only time your light goes off if you close the two switches, then you short circuit the bulb and the light goes off. So for OR and NO, we say that the switches are in parallel. So you have the two switches in parallel, and then all of them now with the lights there, and then like that. So you have the two switches in parallel, and there is your supply. So you have something that looks like this. So what happens here? The only time, this is a OR. The only time the light is off if the switches are open. This is switch A, this is switch B. The moment one of the switches closes, that's O. If A or B closes, the light goes on. If both of them also closes, the light is still on. That's what happens. And the opposite will be no. So with the no, what do? You have the two switches in parallel and all of them in parallel with the bulb. So you have something that looks like that. And then all of them in parallel with the light. So I can just connect my supply like that. So you can easily notice that my bulb is directly already connected to the supply. The only time my bulb closes, if one of the switches, switch A or switch B closes, it's going to short circuit my light. So if my lights are open, if my switches are open, A is open and B is open, you're going to notice my light X is 1. This is NAND. This is no, sorry. This is no. The moment one of the switches, if it's B or if it's A, closes, my light goes off. If both of them closes, my light goes off also. So that's it. So now, the question in the exam is telling you to draw the circuits. So you're going to have to draw the AND gate switch. So which means we have two switches in series. With the bulb. And my supply is there. So we label them A, B, and above is X, and explain its operation. So its operation is simple. How do you explain this? When the two switches, switch A and switch B, are open, based on the truth table, you can explain this. When switch A and switch B are open, what happens? X is 0. So switch A and switch B, when switch A and switch B are 0, X equals 0. When switch A and switch B, if A is 1 and B is 0, what happened? X is still equal to 0. If A is 0 and B is 1, X is still 0. The only time X is equal to 1 if switch A and B equals 1, then X is going to be equal to 1. That's how you explain this. And how many marks is that? That's 8 points, which is 8%. Just to explain that, that's a lot of points. Okay, so 3.8, draw the IEC symbol for each of the following gates: NOR gates, NAND gates, XOR gates. So we just explained here the symbols for each gate, how you can remember them. We've given you some hint on how you can remember the gate. If you cannot remember, just memorize them. If you cannot understand the hint based on the hint, just memorize them. When you are studying, take your draft paper, practice how to memorize them. It's worth it, because they cover about the logic gates will cover about 10 to 12% of the exam. So it's a lot of point to lose if you cannot even draw the symbol of a gate. So where are we? We're back to our guide. Back to our guides there. So yes, so the circuit logic, we've discussed the circuit diagram of logic gates, so we've discussed all that. Back to the question. So name 4 types of flip-flops. So here I'm going to ask you to go through each one of this guide and go through your notes, your textbooks, and answer all these questions. So you should be able to study, explain the operation of RS, draw the diagram, everything. So one of these, unfortunately, they will have to ask you only 1 or 2 questions based on the flip-flops, but you have to study this whole thing. So yeah, that's how it is. So let's try to journey into they say 3.9, name 4 types of flip-flops. That was easy. The types of flip-flop that we studied, you can see that from our guide. The types of flip-flop, we had types like RS flip-flop. So if I have to list here the types of flip-flops, so there are 4 types. We have RS flip-flops, we have D-type flip-flop, and we have T-type flip-flop, and we have JK flip-flop. So these are the types of flip. This was the easiest question. They might ask you just as easy as it is here, and then make a construction drawing of SR flip-flop using NOR gate. So you have to refer to our guideline here. We are here actually. Draw the diagram of an RS flip-flop using NOR gate. So you have to study also the one that using NAND gate. You have to study all this guide. So we never know which one is going to be there. But yeah, that's it. So let's journey into question 2022 question. We're not going to solve all the questions. The ones that we have done already, we can just pass them. So for example, 3.1, state 4 advantages of a digital system compared to an analog system. We have listed that in our guideline. We are on module 13 here, where you have to list some advantages. So we have done that. And then define a positive logic. So we discussed about positive logic and define a positive logic. So with a positive logic, we say a more positive voltage represents a 1, and a less positive voltage represents a 0. That's a positive logic. If they ask you about a negative logic, you say a more negative voltage represent a 1, and a less negative voltage represent a 0. So that's how it is. It's so easy. 2 points, I can say, for free. So we have 2 questions here. One, we have to convert from binary to decimal. Okay, so this there was a mistake here. So they said convert 11101, which is base 2, to binary. We were supposed to convert it to decimal. That was a mistake. And then convert 568 base 10, which is decimal, to binary. So this is what we're doing. We're converting 1111101 base 2 to decimal. So there was a mistake there by the examiner. So it's in decimal. So we want the answer in decimal, which is base 10. We want the answer in decimal. So let me check that I got the correct question. So it's 11101. So that's correct. 11101 base 2. So from decimal to binary, it's actually very easy. What you have to do is you count the digit. So from decimal to binary, it's very easy. You just have to count the digits. So how many digits that this number has? 1, 2, 3, 4, 5. So 5 digits. What do? You just draw the table with 5 vertical line. 1, 2, 3, 4, 5. So that's what we have. And then you write to the power 0 is 1, to the power 1 is 2, to the power 2 is 4, to the power 3 is 8, to the power 4 is 16. So we have 5 digits. If you start from to the power 0, your highest is to the power 4. That is 16. Now, what do? You take this number that we wanted to convert, you fit it on the table. Let me use a different color. Let me use color blue. So I'm going to fit that number in the table. 1, 1, 1, 0, 1. So then my next step, what do? I'm going to take this number here and multiply them by the binary number. That's what I'm going to do. Multiply. So, and I'm going to write my answers here. So that's what I'm going to do. So that's it. So let me go back to, right? So 16 multiplied by 1 is 16. 8 multiplied by 1 is 8. 4 multiplied by 1 is 4. 2 multiplied by 0, that is 0. 1 multiplied by 1, that's a 1. And what do I do next? I add them all up. So I'm going to add them up, add them up, add them up. So 16 plus 8, that's 24, plus 4, that's 28, plus 1, that's 29. So our answer here, let me verify that, 12, 28, that's 29. So our answer is 29 in base 10 actually. So that's it. And let's go back to the question paper. 3.4, if I have to do 3.4, 568 base 10 to binary. So if we have to solve this to binary, so first of all we did that. So this to binary is going to be, so 568, so we are converting 568 base 10. So we want the answer in binary. So 68. We want the answer in binary. Is that correct? Let's check. Yes. 568 base 10. We want the answer in binary. So what do? Apply the same table method. But now when we are going from decimal to binary, we don't know where to stop. We just start drawing our lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't know where we should stop. Why? Until we start filling in the numbers. So we start from right to left. 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16. 2 to the power 5 is 32. 2 to the power 6 is 64. 2 to the power 7 is 128. 2 to the power 8 is 256. And 2 to the power 9 is 512. If we have to go 2 to the power 10, it's going to give us 1024, if I'm not mistaken. And you can see it's already bigger than the number we want to convert. Our number that we want to convert is 568. So we cannot go 2 to the power 10. We have to stop at 2 to the power 9, which is 512. 512 is smaller and closer to 568. Now, so from all these numbers obtained here on the second row, which one, when we combine together, will give us exactly 568? Which numbers? So we're gonna have 512 plus 256 is gonna be big, plus 128 is gonna be big also, plus 64 that's also big, plus 32. We can start with 32, so we can start with this one, plus 32. It gives me 4 and 544, plus 16. It gives me 0 there, 1, that's 6, 560, plus 8, it's gonna give me 568. So I cannot continue because I got exactly 568. So which number did I use? I used 512. I'm gonna put a 1 there. I used 32. I'm gonna put a 1 there. I used 16. I'm gonna put a 1 there. I used 8. I'm gonna put a 1 there. I used, okay, that was the last one I used, was 8, and the rest I'm gonna take 0, 0, 0, 0, 0, 0. So my final answer, 568 base 2, gives me 1, 0, 0, 0, 1, 1, 1, 0, 0, 0 in base 10, in binary, sorry, in binary, in base, this was base 10, sorry, base 10 here, and here in binary. So that's my final answer. Good. Let's go back to the paper. Calculate the value of the following binary numbers. There is addition and there is subtraction. There is addition, there is subtraction. So we did not do subtraction. We only did addition, and it's 2 marks each. So we only did addition, we did not do subtraction. So I'm gonna have to do that. So the first question is, I'm gonna have to redo addition quickly. 1111 plus 100. So 1111 plus 100. So that's what I'm gonna do. So 1111 plus, this is base 2, 110, I guess. 110, yes. 110 base 2 also. So we want to write it like this. We want to write it 1111 plus, we're going to start with the last digits 011. The reason we're doing that is we want to fit the last digit of the second number to align with the last digit of the first number. So, and then you can see there's empty space there. So our rule still remains the same. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 0 carry 1. So 1 plus, so we follow the same rule, follow this rule here. 1 plus 0 is 1. 1 plus 1 is 0, we carry 1. Now we have 3 ones. So 1 plus 1 is 0. We're going to carry already, but we come back here to finish. 0 plus 1 is 1. Now 1 plus 1 is 0, carry 1. And since there is nothing there, we're just going to have to drop this 1 here. Gonna have to drop that 1 here. And that is our final answer. So we have 1101 minus 1001. So 1101 minus 1001. So let's do that. So we have, this is subtraction now. 1101 base 2 minus 01001 base 2. So that's subtraction. That's normal subtraction. It has nothing to do with the ones and twos complement. It's just normal subtraction. Let me check that. I'm good. So 1101 minus 1001. So it has nothing to do with twos complements. First of all, we discussed the rule of subtraction. 0 minus, so if you want to have more clarity on the subtraction, go check some of our previous tutorial. We have explained that with clarity. So we're going to try to just list the rule again. 0 minus 0 is 0. 0 minus 1, this is where we have to borrow. So we're going to write a 1 there, but after borrowing. 1 after borrowing a unit from left. So we're going to explain what does that mean. And 1 minus 0 is 1, and then 0 minus 1, 1 minus 1, 1 minus 1 is 0. So that's what we're dealing with. So if we fall into this case here where it's 0 minus 1, we're going to have to explain. Otherwise, go check our previous tutorials about subtraction, binary subtraction. You're going to have more clarity there. Okay, so let's proceed. So we are doing 1, 1, 0, 1 minus 1, 0, 0, 1. Good. So minus is there. So we follow the rule. 1 minus 1. We are here. 1 minus 1 is 0. 0 minus 0. 0 minus 0 is 0. 1 minus 0. 1 minus 0 is 1. 0 minus 1. 1 minus 1. 1 minus 1 is 0. So our final answer is this. So we didn't have to stress about borrowing a unit. So our final answer is this one. Good. So next question. 3.6. Use one's complement to subtract. So we've done a lot of one's complement. I believe the ones that we've done will easily compensate for this. So if you notice, they say subtract 1001 from 1001. It's kind of the same as the one we did, if my memory serves me right. So we are actually doing 1001 minus 1011. So that's what we are doing there. So I think we have solved this problem if my memory serves me correctly. And 3.7, define odd parity. We have defined this. So odd parity, it's the extra one that must be added to a word to have an uneven number of 1. So that's it. And 3.8, draw a fully labeled switching circuit of OR gates. Now they ask you and they just ask you to draw. That's 4 marks. They didn't ask you to explain. If they had asked you to explain, that would be 8 marks like the other one. And then here, draw a circuit diagram of a RS flip-flop, again using NAND gates. The first question we saw was asking you to use NOR gates. Here they're asking you to use NAND gates, and then sketch the IEC symbol of a D-type flip-flop. So I think we have covered everything we needed to know about question 3. We have covered all the modules and all the important things that we need to know about question 3. I think that will help us a lot. 35% is a lot, so we have to work hard on question 3 also. Thank you.